Hello, everybody. We're going to go ahead and get started. My name is Matt Delacluse, Operations Director of Rayco Rents. Welcome to our webinar on best practice for sampling pump calibration. Our presenter today is Aaron Apostolico. In this 45-minute webinar, he will cover the following: the importance of reliable sampling pump calibration, using calibration data to anticipate pump performance issues, supporting documents for calibration, new advancements in pump calibration technology, and then at the end we'll do a your question answered with Q&A. Aaron serves as product line manager for occupational health and industrial hygiene instruments at Sensidyne. He has proven experience in evaluating safety hazards, risk analysis, safety program audits, compliance review and development, and importance of safety programs. He holds a Bachelor's of Science degree in Environmental Science from Rutgers University and attended University of South Florida's College of Public Health for graduate studies in occupational health and safety. He holds professional designations as Certified Industrial Hygienist, Certified Safety Professional, and Certified Indoor Environmental Consultant. We welcome Aaron back as a speaker and thank him for sharing his knowledge during this exclusive session for our customers. Welcome, Aaron.
Thank you, Matt. Again, it's a pleasure to be here, and I really appreciate the opportunity to share knowledge throughout the industry. It's really a great program that Lesman and Rayco Rents puts on to again educate their end users and again others in the industry. As Matt mentioned, today we are going to be discussing calibration best practices. I'll also be talking about some advancement in calibration technologies that might be useful to some of our end users. To get started, we're going to cover really what do I mean by reliable calibration, what supporting documentation is needed to provide both data integrity as well as supporting any potential legal aspects associated with your air sampling. And then we'll talk about these advancements in technology in today's new calibrators. So the presentation, as I mentioned, will cover calibration records and record keeping as it should be maintained excuse me, as part of the overall process. And then we're going to talk about specifically air sampling calibration technologies and methodologies that will allow users to track pump stability and to create permanent reports in defense of the sample integrity. So to begin, we really need to focus on what is calibration. Calibration is actually adjusting a device to meet the manufacturer's specifications that are within the industry standards and requirements. Most of us think of calibrating as setting a flow rate on an air sampling pump. While this is very true, calibrating really is making sure that when we set the flow rate to whatever flow rate, let's say 2 liters per minute, that 2 liters per minute is really representative of a true 2 liter per minute flow rate. Now, calibration is also defined as the issuing of a report or certificate of calibration that declares a product's conformance with specifications and standards. It's this second definition of calibration which is more properly referred to as certification. And this is really the certificate that comes with your calibrator, which makes it traceable to a higher level. So in talking about reliable calibration, we'll go over third-party traceability, we'll go over accuracy, precision, and the stability of both the calibrator and the source, the pump, that it may be calibrating. So third-party traceability relates to an agency ability to standardize units of measurement. So worldwide, there are national meteorological institutes. In the United States, we use NIST, which is the National Institute of Standards and Technology. It's a division of the U.S. Department of Commerce. When we see things that are NIST traceable, which you'll want to see on your calibration reports, it means that it is brought up to this higher standard that can really be compared. Also, they use a master volumetric device for primary calibrators. And we'll talk a little bit about what separates a primary calibrator from a secondary calibrator as we move forward in this presentation. More recently, we have third-party traceability that will cover or be covered by the ISO IEC 17025 accreditation. Now, this is the main international standard used by testing and calibration laboratories, and it basically says that labs must hold this accreditation in order to be deemed technically competent. We'll talk a little bit more about technical competence when it comes to your calibration devices, again, as we move forward. The National Meteorological Institutes are at the top of the measurement equipment hierarchy. They represent the basis for determining the values of all subordinate standards of a measurement quantity. So in this particular case, you see the NMI, then below it you'll have an accredited calibration laboratory, you'll have your calibrator, which will come with that traceable certificate, and then you'll use that calibrator to actually calibrate your field measurement or your field device for airflow, whether it's a pump or another type of air source. These NIST standards, which I mentioned are part of the U.S. Department of Commerce, are responsible for really overseeing consistent international systems of units. All right, so the term SI. NIST is also charged with imparting these standards to the American system of measurements through calibrations and other services. So these NIST standards will really make sure that when we say, you know, a foot is a foot, a pound is a pound, a kilogram is a kilogram, 1 second of time is 1 second of time, it makes sure that everything is aligned to this national standard, which then can be realigned to worldwide standards. So countries around the world will utilize their own regional meteorological institutes and laboratories to set the basis for their own standards of measurements. Because of this hierarchy, a traceable calibration will exhibit an unbroken chain of measurements all the way to this national measurement standard. So even if there's other parties that are maybe certifying the manufacturer that produces the instrumentation, that certification will be able to be traced all the way up to a national standard of measurement that can be used really internationally. All the measurement results obtained with traceable measuring equipment are traceable to this standard and are also comparable to each other. This allows for measuring equipment that is traceable to both national standards and international standards to have the worldwide comparability of the measurement results. Sometimes we actually ship equipment worldwide for use, and we want to make sure that when we put in a unit of measurement that it is, you know, a traceable unit, that it will be both understood and accepted from national organizations worldwide. The provider of the NIST traceable measurements may be NIST itself or another organization. As I mentioned, manufacturers who manufacture the calibrators and the air sampling equipment will use these traceable measurements to the NIST standard. A lot of times they have a primary set of calibration devices that they'll then use to calibrate their other production equipment. This traceability can be audited by third-party agencies as well. An example of a third-party agency here in the United States would be A2LA. They can provide an accreditation to a manufacturer stating that it follows the necessary procedures and it has the NIST traceability so that the instrumentations that they produce and sell will meet these high standards. The ISO standard, which is the International Organization for Standardization, who has ISO 9001 and 17025 standards, are used around the world as the preferred criteria. They form the basis for guiding the calibration and certification process. Scientists and industrial hygienists will utilize these standards to ensure occupational health sampling is both reliable and the results of the sampling can be used with confidence. The ISO 17025 standard specifically addresses these requirements for competence of testing and calibration laboratories. In most major countries around the world, the 17025 standard is the one which is most widely used and accepted for laboratories to be deemed technically competent. In many cases, suppliers and regulatory authorities will not accept test or calibration results from a lab that is not ISO 17025 accredited. So it's definitely one of those certificates that you want to make sure your laboratory equipment and or your field calibrator has met these high standards. The essential characteristics of a calibration certificate is both the traceability of measurement results and therefore its international comparability. It's important to note that there can be several types of certificates that are offered on the market to document the accuracy of measurement. Not all of these certificates are 17025 certified, although they all should be NIST traceable. The 17025 accredited certificates, again, will have additional data and factors of uncertainty. It is the statement of measurement uncertainties, which includes the determination of the measurement process. Independent assessors must also examine the suitability of the process and the measurement process in order to assure traceability. So again, this is where we say that a third-party audit needs to be completed for these ISO certified laboratories and manufacturers to ensure that the traceability and the process of calibration is being met. According to the international agreements, ELAC, only inspected laboratories accredited to the ISO 17025 standard are permitted to carry out traceable calibrations and thus guarantee complete international comparability of calibration results. So you'll see at the bottom of this the ELAC certification, and again, you'll usually find this accompanied by the ISO 17025 certificate, as well as information like the A2LA certification. User or field calibrations are more accurately defined as a calibration verification rather than an actual calibration itself. So it's important to note that when we do these field verifications, it has a little bit different of a connotation to it than an actual calibration of an instrument where you are making adjustments to the calibrated process. Next, it's really important to discuss accuracy. All right. When we air sample for environmental and occupational health purposes, we have to be able to depend on the results. All right. The equipment that we utilize must be properly calibrated in order for us to feel that the true measurement taken is accurate. Through calibration, adjustments are made to a piece of equipment to ensure that this performs as expected and can be relied on to deliver predictable, accurate results that meet these standards. The accuracy of a calibration device or calibrator should be at least 2 times greater than the equipment being calibrated, although 4 times greater is the preferred minimum. The equipment usually has a calibration range over which the end user will check the specifications. So when you purchase a calibrator for use, it's important that you make sure that the calibrator's accuracy is at least 2 times the minimum accuracy that you need. And again, 4 times more accurate is the preferred. An example of this would be if I need to make sure that I am plus or minus 5% within my set flow rate, I would want to make sure that I'm using a minimum of a 2% accurate calibration device, but a 1% accurate calibration device, known as a primary standard, would probably be my preferred calibration device. Now, accuracy and precision are two different ways of measuring targeting. Although accuracy is intuitively understood and desirable, precision is often confused with accuracy, where the measurements are not representing the true value. If successive results agree, a false sense of confidence may be formed that is not merited. So basically, if you're looking at your calibration results and your live flow readings are coming up very close to each other, we might think that this is an accurate reading. However, this is really stating that the precision of the sample readings are very close together and tight. So you can be accurate, but not precise. So in the illustration I have at the bottom of this slide, you can see that the first target is showing both accurate and precise. The second target is showing that it's not accurate, but a very tight grouping of sample results. So this is not accurate, but precise. The third one is showing that it's accurate, but not precise. Because if you actually averaged out those 4 sample sets, you would get a very accurate result. But there's a lot of instability in that, so the precision is not there. And then, of course, the last target is showing when you have not accurate and not precise, and we want to avoid this at all costs. But really, the latter 3 should be considered unacceptable. We really want to be both accurate and precise when performing our air sampling calibration. So when considering the accuracy of your calibrator, several basic questions should be considered. Who calibrated the calibrator? All right. Was it calibrated by a competent, trained individual? Do I have a signed and dated calibration certificate? All right. What was my calibrator calibrated against? Do I have a calibration certificate that references a NIST traceable master device? Can the laboratory provide the traceability documentation if requested? And then really think, have I ever challenged the calibration lab to ensure that they actually are using traceable measurements? Some additional questions that need to be considered would be, when was the calibrator last calibrated? Is the date of the last calibration printed on the device or on the certificate? Now, this is an important aspect because calibrators get brought out in the field, they get bumped, and they may actually have slight deviations to them. Over time, drift can occur within your calibration device. So it's important that when you send your calibrators back, you follow your manufacturer's recommendations. At Sensidyne, we recommend that calibrators are calibrated annually. I can tell you that most regulatory agencies also require annual calibration for their calibrators. All right. Minimum is usually an annual. Some companies may actually prefer more than annual calibrations take place. Now, when you send them back, some companies just require calibration and a return of device. However, to get the most out of your calibration, you may want to request as-found data also be reported back. Now, some manufacturers or calibration labs will charge additional for this service. However, it's a valuable piece of information to understand how much drift occurred since the last time your device was calibrated. Some additional questions would be where it was last calibrated. Did the calibration laboratory have a 17025 certified program? Was it audited? Did it pass its audits? Also consider, has anything changed since the calibration equipment was last used? Sometimes as we take calibration equipment out to the field, we take it back, it gets moved from one location to another. Damage could occur to your calibrator. Can my calibrator be checked in the field to ensure that it is still performing as expected? One way to confirm this is by performing an internal leak test if such a leak check is possible with your calibration device. Some other things to consider regarding precision. When considering precision of your air sampling calibration, you must also take into account any factors that could introduce bias to your sampling flow rate. This may either come from equipment being calibrated, the sampling train, the calibrator, or the environment in which you might be calibrating. So we talk about, can a calibrator be accurate but not precise? Well, many different things can influence why it might be accurate but not precise, or precise but not accurate. One of the things we should consider is constant flow. All right. We may also want to consider if we're looking at volumetric versus STP, which is a standard temperature or pressure, which may be referenced, or if pulsation can impact the flow rate itself. And we'll talk a little bit more about these three aspects that could relate to the precision of your calibration for field instrumentation. So for constant airflow, most air sampling pumps these days operate in a constant flow mode. This means that the pump will maintain the same flow rate regardless of the back pressure that accumulates. And then it must stop running when the flow rate goes outside of the required accuracy. This process works a lot like cruise control on your car. The pump will sense when the flow rate is trying to drop, similar to a car driving up a slope, and it speeds up the pump's motors to maintain the desired speed or set flow rate. Now, industry standards require the actual flow rate to be within 5% of the set flow rate, which means when you do your pre-calibration and you set your desired flow rate, your post-calibration should be within 5% of that set flow rate when you started. Now, if your pump is yawing a bit, which means it'll rev and you'll kind of hear the pump trying to accommodate for a noticeable change in pressure, it'll start revving, going row, row, row. All right. This means the motor is probably trying to compensate for an observed change in back pressure. In some cases, this can be pulsation caused by the pump. It can be caused by tubing or the media holder. If you're using a cyclone or another type of media holder, this could also contribute to it. In other cases, it can be attributed to the calibrator being used to calibrate the pump. Now, these biases can affect the average flow rate based on the pump's attempt to maintain constant flow. So if your pump is trying to constantly change, you're not really seeing a stable result in your calibration readings. So if you're taking multiple samples, you may average out to get an accurate measurement, which is what your desired flow rate is, but it might be really going really high, really low. It could change the accuracy. And if you're making adjustments to the pump based on this, when you disconnect it from your calibrator, it might actually be flowing at a different rate than what you saw while it was connected to your calibrator. Environmental factors may also impact the precision and accuracy of your calibration results. It's important to understand the relationship between pressure, temperature, density, and volume when performing volumetric calculations. It should also be noted that gas measurements are related by the material's density, which depends greatly upon pressure, temperature, and to a lesser extent, the composition of the air that is being passed through the calibrator. So when we talk about these relationships, you must note that gases are compressible and will change volume when placed under pressure, when they're heated or they're cooled. Now, a volume of gas under one set of pressure and temperature conditions is not equivalent to the same gas under different conditions. This relationship can be illustrated by using the combined gas law, which is derived from the ideal gas laws, also known as Charles' law and Boyle's law of classic chemistry. So we'll talk a little bit about some of these laws and how they will relate or impact your air sampling calibration. The ideal gas laws are utilized to normalize gas volumes and/or volumetric gas flow rates. This is a volume per unit of time to a particular set of temperature and pressure conditions, because the volume of gas, of air in most cases, is a function of the temperature and pressure conditions at which the gas exists. So Charles' law says that the relationship between volume and temperature is inversely proportionate. So the volume of an ideal gas, when the pressure and molar mass are constant, is directly proportional to the absolute temperature. So as temperature increases, the volume of gas increases. Now, Boyle's law says that there's a relationship between pressure and volume. The pressure and volume of an ideal gas are inversely proportional. While one increases, the other decreases, when the temperature and the molar mass of the gas are kept constant. So here we say that the volume is inversely proportional to the pressure. The combined gas law will use all three of these elements, pressure, volume, and temperature, to basically state that when any of these environmental factors are changed, it will impact your resulting volume. It's important to note this so that your conditions that you're actually calibrating to before your air sampling are represented to the conditions that you would be calibrating post your air sampling event. It's important to also note that when we are measuring pressure and volume and temperature, that we're using consistent units of measurement. So here we talk about ambient pressure, air volume in liters or cubic meters, and temperature should be denoted in Kelvin, all right, which is equal to, if you were using Celsius, 273 plus your degrees Celsius. Now, assuming the makeup of air is constant, changing the temperature or pressure will change the volume. However, in the case of volumetric devices with a fixed volume, all right, which are several of both the wet cell and dry cell calibrators, which are primary calibrators, what changes is the speed at which the gas moves through that fixed volume. Therefore, it's really important to understand if your calibrator calculates the impacts of temperature and pressure on the airflow. Now, the calibrator can do it, or the industrial hygienist or the person collecting the sample must understand how to perform it. So we're really comparing apples to apples. Another aspect to consider is correcting the volume based on a reference STP or NTP, or to a referenced STP or NTP, which is your standard temperature and pressure. Typically, this refers to nominal conditions in the atmosphere at sea level. This value is important to physicists, chemists, engineers, and pilots. It's also important to industrial hygienists. It should be noted that different agencies around the world determine their own STP values. So, knowing that you have different STP values used in different locations, it's important that whenever you convert to an STP value, that you actually state which STP value you are referring or referencing. One of the agencies, IUPAC, which is the International Union of Pure and Applied Chemistry, and the National Standards and Technology, NIST, are just two of the universally accepted standards. IUPAC defines STP with a temperature of 273.15 Kelvin, which is roughly 0 degrees Celsius or 32 degrees Fahrenheit, and an absolute pressure of 105 pascals. So in order to correct the volume to a reference standard temperature or pressure, or NTP, which is normal temperature or pressure, the following equation will be utilized. Your referenced volume, which is denoted here as V sub S, is going to be equal to your measured volume times your measured ambient pressure times your referenced temperature divided by your temperature of the sample which is measured, times your ambient pressure. And I know this can get a little bit confusing to do manually, but it is something that you may want to, again, standardize your volume and hence your flow rate so that you can actually or accurately measure whether or not your pre and your post calibration is truly within that 5% margin. Again, when you're measuring standard temperature and pressure, make sure that you're not confusing it with normal temperature and pressure. Again, in the United States, NIST and the EPA lists normal temperature and pressure as 293 Kelvin, which is really measured at 20 degrees C or 68 degrees Fahrenheit, and an absolute pressure of 101.325 kilopascal, which is 760 millimeters of mercury, or about 14.7 psi, or if you're measuring in inches of water, it would be 29.92, just under 30 inches of water. The NTP values are commonly substituted for STP, which is acceptable. The key takeaway here is whatever you're using to standardize your volume in your pre-calibration, you should use and cite that same standard when you are using to convert your post-calibration volume and or flow rates. A next important factor really to talk about is the stability of your calibration. During air sampling, end users strive to have consistent airflow across the entire sample period with that max deviation of 5%. The closer the deviation is to 0, the more accurate the calculated volume is over that period, noting that volume is a function of flow rate and time of sample. This is again why you might want to use an STP or NTP conversion when looking at your pre-calibration and post-calibration sample results. Now, why are stable readings important? Again, to make sure that pre and post calibration remains within the plus or minus 5% of your desired or your initial set flow rate, and to ensure that back pressure artifacts from your calibrator are eliminated wherever possible. So think about every cycle of the air pump. Air is drawn in and then exhausted through the pump. The resulting airflow will not be completely smooth, and it includes an alternating or pulsating component. Now, due to the pump's action with several types of pumps or most common pumps out there, which use a pneumatic system to create the vacuum and positive pressure that your pump produces. The pulsation performance is expressed as the ratio of the pulsating component amplitude to the mean flow rate. Now, why is this important to me, or why do I care about the stability of my pump? Well, as sampling heads like cyclones rely on a very steady flow to maintain a specific cut size, it is important that pulsation to be kept to as little as possible. Now, deviation from the specified airflow for a cyclone will result in the sampled air not accurately reflecting the respirable size fraction or the thoracic size fraction or the inhalable size fraction, depending on which type of device you are utilizing. The further that you move away from that manufacturer's required flow rate, you can either undersample or oversample the sample size, and therefore you would not have a representative size-selective sample. Now, with some piston-style calibrators that are on the market, the piston itself can actually create an artifact back pressure pulse, which the constant flow pumps will then respond to when they're in their constant flow mode. And this could create that yawing effect that I talked to about earlier. So this is where your pump will really start, revving up and responding to that change in back pressure. This will really create an unstable flow, and you want to have as stable flow as possible when you're recording that flow rate on your field log. Now, in the case of these mechanical pistons, so this would be a dry cylinder where a piston moves up and down through a cylinder. The piston moves from the bottom position. It can get drawn up until it passes the start, and then it'll pass a stop sensor. When it passes the stop sensor, it falls back down to the bottom of the cylinder in a free fall. It's this free fall that can create a pulse that can actually be seen or affect the pump itself. The end result is that the flow rate is variable under the conditions biased by the calibrator, which will not be present when you disconnect the calibrator and the pump is running. So what's happening is you'll actually see a different flow rate when the calibrator is connected to the pump with these piston-style calibrators. Ideally and more correctly, the piston should move up and down the cylinder at the same flow rate so as not to cause the disturbance of the airflow. Another key element or best practice associated with air sampling calibration is record keeping. Now, I know record keeping can be daunting and tedious, but it's a very important part of maintaining sample integrity. It's also important for your report preparation if your air sampling results need to be assembled into a report and presented. It's also important for legal purposes if your air sampling results are ever challenged. So what does support documentation for air sampling typically consist of? Well, you have a chain of custody, you'll have your field notes, and some of the field notes should include items like a pump model, your pump ID, your sample ID, your worker area ID, your start and stop time, your flow rates, your volume, and then relevant activities. And an item that easily gets missed but is very critical for the defense of your air sampling results is a calibration log. So documentation and record keeping are fundamental aspects of air sampling. In order to maintain integrity before, during, and after a sampling event, the operator and facilitator must record relevant data that corresponds with that event. There are several key documents that should be maintained as part of every sampling event. As I mentioned, these include your calibration log, your field notes, as well as the chain of custody. These three documents are interrelated to one another and have overlapping information that should be consistent across all three. The calibration log has very specific details that should be captured as it relates to each pump and sample used during calibration. So these sometimes either get forgotten or sometimes get caught up. A lot of times they are integrated into your field notes, but the calibration log should at minimum record the date and time of your calibration, the pump model that is being calibrated, the pump serial number, the username, the sample ID, the calibrator ID, the date of the last calibration for your calibrator, the temperature and pressure at which you're calibrating, the flow average, all right, whether it's volumetric or the flow average in STP if you're converting it, the number of samples in your average sample set, the standard deviation of those samples to make sure that it is precise, and then the flow rate readings themselves so that you can go back and actually look at if there were any inconsistencies or strays amongst your sample set. So this is typically what a calibration log should consist of, where all of those items that we just went over are really spelled out. With some of the newer devices and newer technologies, it will actually allow you to input information into your calibrator to produce a calibration report such as the one seen here. Some additional supporting documentation that you want to hold on to is your calibration document for your calibrator itself. Now, this is a certificate that your service provider or manufacturer provides. Maintaining a copy of the calibration certificate is essential for identifying measurement uncertainty guard-banded and acceptance limits by the accreditation body, as well as other provided specific details associated with your calibration device. Your field notes should capture precise details about the sampling event. These details should align with those in your calibration log and incorporate those activities specific to the pump and media that was used in your calibration. These details generally include your pump model, your pump ID, your sample ID, your worker or area ID, the sampling method, your media, your start and stop time, your flow rates from your calibration log, your final volume, and whatever relevant activities. Now that supporting documentation, once your post-calibration process is completed and documented, will be transferred to your chain of custody. While many chain of custodies vary in format, common details are required. These details generally include your customer information, your turnaround time, your sample ID, your date sampled, your collection media, your sample volume units, your analysis type, your analysis method, and then your relinquished and received by information. Note that a lot of these pieces that go onto your chain of custody should align with your calibration log as well as your field notes. Now, these documents should be kept on file together along with any corresponding lab report that is received back, as the data may need to be reviewed at a later time and or analyzed for consistency or used for comparing historical data sets. In some instances, the data may be challenged in legal action where the supporting documentation must be defensible. I can tell you as an industrial hygienist of about 20 years in the field, I've actually had several of my air sampling reports challenged, not necessarily because they thought that I was inconsistent, but because an employee ended up contracting an occupational related illness, and they wanted to identify if there was a relatedness of the illness to their occupational exposures, at which point I was called in as an expert witness to defend the air sampling results that took place. And again, a lot of these questions that are answered by the legal counsel or that are asked by the legal counsel will include things like, when was your calibrator last calibrated? Who calibrated it? Was it traceable? Do you have the documentation showing the traceability? How does it interrelate to the air sampling event that was performed on the day that you claimed the results were as provided? So having all this supporting documentation, while again it sounds tedious and monotonous, can be essential if and when it is brought into question. Be mindful of transcribing notes when performing your air sampling calibration. Often pump identification, calibration data, and sample name can get mixed up, especially when collecting multiple samples simultaneously. Time-stamped digital documentation is much more reliable than handwritten field notes from 5 years ago. When applicable, download data, transcribe the handwritten field notes, and keep electronic files indefinitely unless your particular program requires or dictates otherwise. Now let's talk about some advancements in calibration technology. Over the years, many advancements have taken place. Although soap bubbles are still used in volumetric burettes today, technological improvements allow users to increase convenience while still maintaining that high accuracy, precision, and stability, using advanced circuitry and sensors which have been integrated into today's instrumentation. Now, newer primary dry cell calibrators, which were introduced to the market, can be configured to meet users' calibration needs. These calibrators are more convenient to use compared with the older soap bubble calibrators, which are also primary, primarily due to eliminating the need to manually generate the soap bubble from the soap solution. So one of the larger complaints that I've heard and I've experienced in the field over the years was, while the accuracy of a bubble generator, because there's virtually no resistance of moving an air bubble through a column, is very precise, and for that reason heavily relied on. Having to depress a plunger over and over again to collect your sample can become monotonous and very repetitive in the field. So newer calibrators on the market, dry cells, can eliminate the need to produce individual soap bubbles. Some additional advancements that are in the market allow users to select between continuous or averaging modes for your calibrator. In an averaging mode, the user may select a specific sample set to be averaged. Now, in general, I would propose that more samples are better, but sometimes time does not permit. I would normally suggest taking a minimum of 5 samples in your sample set to get an average reading. However, 10 is probably preferred. However, your particular program may dictate more. The user can define the engineering units as well, as looking at things like the date, the time, the temperature, and choose from a selection of languages in the device's library. So all of these are important, and make sure whatever units of measurement you start with when you're calibrating, you're recording down the same units of measurement in your post-calibration data. So we're really comparing apples to apples. Some additional advancements allow the user to take full advantage of internal sensors for standardizing flow rates based on those reference temperatures and pressures. As you saw earlier, there were some complex equations that were utilized. Well, some of the newer calibrators on the market will actually do those conversions for you to eliminate the calculation mistakes that could occur by doing this manually. Additionally, some onboard computing can data log the calibration events and perform statistical analysis on the deviations between the readings. So earlier we talked about precision. Well, how do I know that my readings are actually very close to one another? All right, very, on that targeting that we saw earlier, that we have a very close, shot group. So one of the ways we can do that is we can look at the standard deviation or the percent deviation between each sample measurement. So some of the new calibrators on the market will actually show a 2 sigma standard deviation, and you can actually set this. Typically, I like my individual samples to be under 2.5%. I've seen where you're using a cyclone device that you want more accurate. You may set that at 2% or even as low as 1% requirements. But generally, readings under 2.5% are going to be acceptable. The reason why I choose 2.5% is if the variation was as much as 2.5%, you could have a plus or minus 5% error from your start and your stop reading, which is, remember, the percent deviation that we want between our pre and post calibration. Some additional advancements also improve the user interface capabilities. One of the calibrators on the market has full touchscreen keyboards, which will allow users to actually input data about their pump, as well as these user-defined fields for maintaining the sample integrity. It's important that your calibrator also provides specific information about the calibrator, and if it's a 2-piece calibrator, both the base and the flow cell, when it was last calibration, when calibration is next due, if there's firmware versions or updates that could be involved, as well as, does it have good battery health or filter health if your calibrator has such devices. Now, the newest piston-style calibrators have pulse-free valve technology. This can provide a low back pressure to the devices being calibrated. Now, this is specific to a Sensidyne product where you see stable flow. This is part of Sensidyne's newest release, Calibrator 3 calibrator. Now, this unique patented design will equalize the pressure on the pump regardless of the puck travel direction. So if you are looking at the piston as it's moving up and down the cylinder, you'll really see that it doesn't touch the bottom or the top. It really oscillates in the center of the cylinder, moving up and down at the same speed. Also, the Calibrator 3, as shown in this picture here, uses a fixed sensing array technology. So what does this do? It eliminates the potential for misalignment of photosensors. As I mentioned earlier, some other dry cell calibrators will use optical sensors at the bottom and at the top of the cylinders. However, if these sensors become misaligned, your readings will be invalid, and usually they'll have to go back to the manufacturer or a repair center to be repaired. A more sturdy solution is a fixed array system, which cannot become misaligned. It can also provide additional data points, as a fixed array system can have more than just a start and stop. It can actually measure the movement along the whole fluid travel of the puck in the cylinder itself. Calibrators now can also generate their own printable calibration reports. The Calibrator 3 is an example of this. These calibration reports display that sample information, saved instrument settings, and individual sample results all within this calibration report. This allows the calibration data to be added directly to your sampling reports and historical records, which can be retrieved and reviewed for later statistical analysis. In the course of preparing this presentation, there were many references and citations utilized. Here are some of those citations. I believe that Rayco Lesman will be providing a PDF copy for those that request it, as well as recording this session that can be viewed by you or your colleagues later. I did want to note that there were, again, many references that were utilized in the creation of this presentation. These reference pages will be available again at the end of the PowerPoint slide presentation. At this point, I'd like to open it up. If there was any questions that were submitted, I'm happy to address these questions in the time remaining.
At this point, Aaron, I don't see any questions, so we'll just go ahead and close. Thank you for your presentation. And then if there are any specific application questions, feel free to give us a call, 866-RENT-EHS or 866-736-8347. You can also reach me by email at matt@raycorents.com. If you want to know more about our technologies we supply, please follow us on social media. We put out lots of good technical tips on my blog at blog.raycorents.com. You can also follow us on LinkedIn and Twitter. We do record all these training sessions, as Aaron mentioned, that you can find on YouTube. Or from our training centers on both the Lesman.com website and the RaycoRents.com website. If there are any topics you'd like us to cover in our webinars, please send me an email with the subject. We have access to lots of product and process specialists. Please let me know what we should cover by emailing me again at matt@raycorents.com. At this point, if there are no further questions, our presentation will conclude. All right, thank you, Aaron. Appreciate it. I don't see any other questions.
Thank you, Matt. Happy to provide, and we'll be in contact.
All right. Everybody have a great day. Thanks.
Thank you.